Exam 2, Essay 1. This video is about lots of different skeletal muscle and smooth muscle movements and contraction filaments. So first I just wanted to talk about how the action potential goes from the cell to the different parts of a muscle fiber or muscle cell, and then go into the fibers inside each of the sarcomeres, which are the individual units inside a muscle fiber, and talk about all the fibers inside of them. So if we start off right here, we have a neuron. It's going to synapse in a muscle cell. What's going to happen is the motor neuron is going to get a signal from brain. This is a myelinated neuron, and it's going to send an action potential. So we're going to have these sodium, voltage-gated sodium channels, right? Oops. And they're going to let sodium in. It's going to depolarize the cell. That's going to open a voltage-gated calcium channel. So with muscles, calcium is everything. So when this channel opens and calcium comes in, we have all these vesicles with snare proteins on them. And when it gets activated, the snare proteins twist up, pull the vesicle outside the cell, and neurotransmitters released. Neurotransmitter that's used here is acetylcholine. So it's going to come to our receptors on the cell. These are N1 receptors, and they're ionotropic, which means to release ions into the cell. These are going to release cations. It's going to let sodium into the cell. This is going to bring the action potential inside the cell. So now we have an action potential inside the cell. So in muscle cells, there's something called T-tubules, which are basically these tunnels of extracellular fluid inside the cell. And so it's not really inside the cell, it's just like a tunnel through the cell. And so this allows the cell's action potentials to reach what is known as the sarcomeres. So inside a cell, for example, let's say we have here, this is called the sarcoplasmic reticulum. In normal cells, it's called the smooth ER. This has lots of calcium in it. Extracellular, we have lots of calcium as well. So we want in the sarcoplasm, we want there to be calcium. We want this to move out. So what happens is there is a protein channel right here called ryanodine. And ryanodine is a protein that is mechanically gated. So it's not voltage gated. So in order to activate it, we have to have another protein, and this one sits in the cell membrane. And so when that action potential comes, it's called a DHP, or the pyridine, sorry. And so this is a voltage-gated channel, a voltage-gated calcium channel actually, but it doesn't let calcium in the cell, it just opens. When this opens, it basically almost bumps the ryanodine channel, which is going to open and allow extracellular calcium to flow out into the cytoplasm, or the sarcoplasm, sorry. And so that's going to flow out, and that's going to cause calcium propagation or a muscle contraction throughout the cell. So inside a cell, if we have our muscle cell here, we're going to have lots of sarcomeres is what they're called. Basically, they're like little units inside the cell, and they have all these fibers in them. When calcium comes into this part of the cell, it causes these to contract, and they get smaller, which causes contraction of the muscle. So inside one of these, we're going to have, inside the sarcomere, we're going to have these little groups of contractile filaments. So we're just going to draw one set of them here. So this is called the Z-disc. This protein kind of holds all the other filaments. So then we have what's known as nebulin. And titin or titin. Now these titans, these proteins aren't actually connected, but they have hydrogen bonds between them, so it almost acts as if it's one filament. So what's going to happen on top of these, we're going to have two things. We're going to have actin, and then we're going to have myosin. So these myosin heads, if we were to draw myosin, it's going to have these two heads. It's going to have two heavy chains and 4 light chains. So for simplicity's sake, typically we just draw like this. So these myosin are going to be on top of the titan. Okay, you get the idea. I'm just going to draw a couple other circles on the titan. And then our actin is made up of G-actin or globulin actin, which is a spherical protein. And when they get into a line, we call it F-actin or filament actin. We get a long chain. So this F-actin is going to come on this nebulin. So I'm just going to draw a bunch of actin. So what happens is on the actin, there's a binding site. And that binding site inside the individual globulins, there's this binding site for these myosin heads. So these myosin heads will grip to it, they'll move and cause filament sliding. So this is referred to as passing filaments or the sliding filament theory. And basically it's the idea that the filaments themselves aren't getting shorter, but they're causing the contraction. So there are some other proteins used to regulate it. So we have what's called tropomyosin. So this tropomyosin blocks the myosin binding site on the actin. So it comes in a certain length, blocking maybe 6 or 7 on here. And then, since that covers that site, we're going to have a third protein, and this protein is going to regulate whether these tropomyosin cover the binding sites or not. This is the Mickey Mouse protein, also known as troponin. So we have 3 subunits here. We have our calcium subunit. It has 2 low affinity calcium spots, and then it has 2 high affinity. So these high affinity points are always filled. However, the low affinity is only full when calcium is rushed in the cell. So then here we have the I and the T subunits. T binds with tropomyosin, the I binds, inactivates the actin, right? So these Mickey Mouse proteins are going to be in here, and there's one for each tropomyosin. So it's going to bind to the actin here, it's going to bind the tropomyosin, and then it's going to bind to calcium. So when calcium comes in, these move out of the way, still attached to the actin, but they move it, allowing the myosin heads here to come in and bind to the actin chain and move along it. And so when the flow of calcium stops, the low affinity points no longer have calcium, and so that then this will return to its original conformation and cover, using the tropomyosin, it will cover the activation sites. So that's kind of how the sarcoplasmic reticulum perpetuates the calcium to all the different contractile filaments and how they work together. So now let's talk about energy. Where does this energy, oh wait, no, sorry. Let's talk about the bridge, the cyclic bridge. First we have to talk about the movement of the myosin. And the way this does this is a cyclic bridge movement, postulate, whatever it's called. So what's going to happen here is we're going to have an ADP inside the myosin head and an inorganic phosphate here. Calcium is going to come into the cell, and when calcium does, the tropomyosin is going to move. Our myosin head is going to bind to the actin, And when it does, it's going to release energy. So we're going to get some heat, and then it's going to break this bond with the inorganic phosphate. So an inorganic phosphate is going to come out, as well as this ADP. So we're going to get a conformation shift. So this is called uncocked, and this is called cocked. When it's uncocked, an ATP is going to come in, bind again. When it binds the myosin head, it's going to break that bond. There's ATP in there. And that's going to release it from the actin. Once again, some of the energy will be lost to heat. Then we're going to go through hydrolysis, where one of the inorganic phosphates will be broken up this ATP and put on to the heavy chain of this myosin, and then we'll restart the cycle. So basically it repeats this over and over and over again, moving from cocked to uncocked to cocked, uncocked, so it can move along the actin chain, causing a contraction in the cell. So this is just for skeletal muscle. We'll talk about smooth muscle in a minute, but I just wanted to cover that. So where does the energy come from, right? We're using ATP here. So where is our ATP source? We have several sources of ATP. In fact, we have 4. Each lasts a different length of time, but they each have their particular uses. So our first type is called cytoplasmic ATP, or sarcoplasmic ATP, right? Because these are muscle cells. So this is just inside the cell. It's just floating around. It lasts about 5 seconds. So any really quick movements. So our eyes use this a lot because our eyes don't need a lot of movement to adjust the iris. It's just really quick movements. So we use cytoplasmic ATP. Next type is called creatine phosphate. So typically ATP will we'll have ADP, and it will add an inorganic phosphate and become ATP. This process takes lots of time, so we don't do it. Instead, we do it later, but we use an ADP and we'll add creatine phosphate, and it will make ATP with less energy. So this lasts about 10 seconds from the beginning of time of muscle contraction. Our third is going to be glycolysis. So this is going to be taking sugars, C6H12O6, and turning them into ATP and pyruvate. So let's not talk about pyruvate, but it's going to create a little bit of ATP. This can typically last about a minute. So then our last option is aerobic respiration. So this is going to last hours, but it takes time. It's slow. These are anaerobic. This requires O2. So because it requires O2, it typically requires more blood flow. More blood flow, more nutrients. And because this blood flow and oxygen are necessary, we see this often in our big muscles. However, these are really useful because they're anaerobic, they're fast. They don't require oxygen, so they don't require as much blood flow. Like in our eyes, right, there's less blood flow, but it doesn't need as many nutrients because it doesn't go through as much aerobic respiration as other muscles do in the body. So those are kind of the advantages and disadvantages and what conditions it'd be used under. So now we're going to move on to smooth muscle. So we have 2 types of smooth muscle. For our purposes, we'll talk about smooth, tonic, and we'll talk about phasic. These are 2 types. So tonic lasts for a long time. These are our sphincters. Phasic muscles go on and off, and it's pretty common for peristalsis, or the movement in our lower intestines. I'm not sure if that's how it's spelled, I'm gonna be honest. Anyway, so your body will go through two different cycles, or these cells will go through two different cycles. And so let's start with phasic. So very similar to our skeletal muscle, kind of has some similar steps. We're going to start with our ADP and our phosphate group here on our myosin head. Calcium is going to come in the cell, but this time the smooth muscle requires more. So we're going to get MLCK, which stands for myosin light chain kinase. Kinases add phosphates and an ATP. And so what happens is this MLCK and the ATP are going to come in, and instead of binding like normal, what's going to happen is this MLCK is going to bind an extra phosphate onto the head. So it's represented right there. Then it's going to stick. It's going to stick right there. And so just like normal, right, our phosphate is we're going to lose some heat. This is going to break. So we're going to get our inorganic phosphate out. We're going to get our ADP out of here, right? But this phosphate group is going to stay on. So now we're going to be in a cocked position, uncocked position. Sorry, this is cocked. This is uncocked. We're going to have our inorganic, or our phosphate on here, right? So now ATP is going to come back into the cell, cause it to release. Sorry, I drew that too close. Now we have ATP here. ATP is going to come in and bind with that head, releasing it. Once again, releasing heat. But we're still going to have our phosphate here. So there are two things that can happen now. We can go through hydrolysis and start this over again, not requiring these things, just skipping over this first step, returning to this step here and continue through this. This is really common for our phasic muscles. However, if, for example, the muscle needs to stop contracting, or just naturally what's going to happen to some of the molecules naturally is MLCP is going to come. So this stands for myosin light chain phosphatase, and it's going to take off the phosphate group. So coming out, we're going to have that phosphate, right? This blue one here, I'll color coordinate. Our phosphatase right there, and it's going to return to this original position. And if there's calcium and MLCK and ATP again, it can continue to go in a circle. So that's kind of what it looks like for our phasic muscles. And now we're going to talk about our tonic muscles. Tonic is a little different. Let me get rid of some of this other stuff. But it's going to go through, once again, kind of a similar process. So we got our actin here. Our myosin heads are going to come and bind to it. So right here, just like as always, we have our ADP. We have our inorganic phosphate right there. And so what's going to happen is, just like with the phasic, calcium is going to come in, our MLCK is going to come in, and our ATP is going to come in, and it's going to do the exact same thing. It's going to bind this head here. We'll get our little phosphate here. We'll get our ADP. We'll have our phosphate. And so now here's the difference. What's going to happen is MLCP is going to come in here, right? So we lost our heat. We lose this, our ADP and our inorganic phosphate are going to come out, but this MLCP is going to take off our phosphase. So now we're going to go into an uncocked position here, but it's naked, it has nothing on it. Sorry, they're bonded. So without this phosphate, it's not going to be able to release. So we go up here, we get some ATP, but the head is going to have to remain uncocked. Sorry, it always remains uncocked, but it's not going to come off. Oh, I made a mistake over here. This should be cocked still, or uncocked, and then it goes to cocked here. Sorry, so this is uncocked. And then it's gonna go through something called the latch period, where what's going to happen is this is basically just gonna stay attached. Eventually it's going to fall off and it's going to return to what it was before, but for a while it's going to remain attached. So this is how our sphincters stay closed for a really long time, is because they go through this latch phase and latch period, and it causes them to stay that way. So these are the two ways the muscles contract, but smooth muscle and skeletal muscle are very different. So here's some of our differences, right? This has MLCK in its process. This does not. No MLCK. There's actually MLCK in the cell, but that's not important. The skeletal muscle only has the one system of contraction. This has multiple systems of contraction. The smooth muscle can use extracellular calcium. Smooth muscle can only use the sarcoplasmic reticulum calcium. This can also use sarcoplasmic reticulum calcium. And I just wanted to show that real fast above. So if we have a G protein here, it receives a signal, right? It's gonna send its alpha and beta and gamma subunits off, and it's going to activate what's called phospholipase, and that's going to send IP3 to the SR. IP3 is going to open our ryanodine channel, and calcium will come out. Whoops, sorry. So that's what's going to happen in our phasic muscles, smooth muscles, as well as our tonic muscles. Besides this, because they need an increased amount of calcium, they're also going to have our dihydropyrimidine channels here. These can be activated by a voltage gate channel, allowing calcium to come in. So this would be in our tonic cells. And so that's another big difference between our skeletal and smooth muscle. And the reason it does this is the smooth muscle has no T-tubules, but our skeletal muscle does have these T-tubules, which allows it to use only calcium from the from the sarcoplasmic reticulum. So those are kind of our big points. Skeletal muscle is also voluntary. There are some reflexes that aren't necessarily voluntary, but our smooth muscle is out of our control. So this is going to be our somatic system. This is going to be sympathetic and parasympathetic system. Right, so those are kind of our big differences between the two. So as we've kind of finished up talking about the smooth muscles, how they contract, as well as all the different types of energy sources, and skeletal muscle, we want to kind of move in and now talk about reflexes. So just to start on the most macro scale, we have our muscle fibers here, right? And they run up and down the whole length of our muscle. And here, not running the full length of a muscle, we have muscle spindles. So there are two types of muscle spindles. Oh wow, that was terrible. These are called bag muscle spindles. These are called chain muscle spindles. they're also innervated by the somatic system. We have here gamma motor neuron. These gamma motor neurons keep tension. But then we also have our sensory neurons, and this is how our motors, or how our muscles get sensory information. So this is our IA and this is our 2A on our chains and our bags. So these are slower and these are faster. Both are myelinated. But that's the big difference. So when we get a fast stimulus, for example, if we get a stimulus, if it's just fast, the bag responds quickly. Bag adapts quickly. However, if we have a long stimulus, the bag, after this initial spike, ignores the rest. But that's when our chain is active. Those chain cells are active and they're going to recognize this continuation. So with these cells, they recognize stretching, and the bag will get the initial and then the chain will get the continual. And so these are in our muscles giving us sensory fibers. So let's draw inside our body. I'll go back to that. Okay, so inside our body, we have our muscles. So let's say, for example, let's start with a stretch reflex. So let's say, for example, here we have our quads, our hamstrings, our foot. And so inside this fiber, if a doctor, for example, hits our leg with a mallet, it's going to stretch. It's going to stretch the muscle. The muscle is going to be stretched, and these fibers are going to feel it, our bag fibers and our chain fibers. So this is our central nervous system. This is our spinal column. This is our dorsal side. This is our ventral side. So we're going to have sensory. Sensory always comes from the dorsal. Sensory, let's use a different color. Sensory is going to come and go to both those muscles, and then our motor is going to come and go to both those muscles as well. So what happens is when it feels stretching in the hamstring, the signal is going to be propagated, right? It's going to come down and it's going to synapse with this muscle here, or with this motor neuron here, and cause this to contract. It's going to cause contraction. So it's going to cause the leg to kick up, right? Then it's also going to send a signal to this cell, but it's going to do it through a secondary neuron. So there's going to be a little short neuron, so this is going to be IPSP to this, and it's going to relax this muscle so then it can kick the leg up. This is going to be an EPSP. So that's stretch reflex. And then we also have what's called withdrawal reflex. So withdrawal reflex is when we hurt ourselves or there's pain. These are called nociceptors. And these feel pain. So we're going to talk about the withdrawal reflex and then the counter extensor. So I'm going to draw again here in the middle, our spinal column. Here's our dorsal side, here's our ventral side. This time let's do a hot plate. So here's our bicep, here's our tricep. Your hand comes down here, touches the hot plate, and it says, ooh, hot, right? So our sensory neurons are gonna come up and it's gonna say, oh, it's hot. So we're gonna have these motor neurons that come out, right? This sensory neuron is gonna synapse with the bicep, And then once again, it's gonna deactivate the tricep. So we have our IPSP here, we have our EPSP here. So it's gonna cause this muscle to contract and this muscle to relax. It's gonna pull the hand away from that hot. That's because these nociceptors, they're gonna feel that pain. But then our counter extensor reflex, right? If we're gonna move our arm up and out of the way, we need to counter our balance. So if we have our other arm over here, with our hand. Sorry, these are terrible drawings. We're gonna have our sensory neurons that go out here, of course. We're also gonna have our motor neurons. So our motor neurons come out the ventral side to each one of those. So what's happening is this sensory neuron, sorry, I'm sure those in the right color. This sensory neuron is also gonna have branches over here. And this time it's going to synapse. Let me get rid of this IPSP. Oops. So it's going to synapse here with this tricep neuron. It's going to cause the tricep to contract. It's going to cause the bicep to relax. So the way it's going to do that is it's going to use IPSP receptor again to cause this muscle to relax. So this is called the counter extensor. It's to help maintain balance. So that'll maintain balance as this other arm contracts. This arm will extend backwards and keep us balanced. So the last reflex I wanted to talk about, this is called, this is called the Golgi tendon reflex. It's kind of the opposite of the stretch reflex. So here's our spinal column. We're gonna use the leg again. In our example, here's our foot. So as this muscle tapers, it has a tendon that comes right here, and in here, here's where our Golgi cells are. So Golgi cells are only in the tendon, and they respond to tension, not stretching. So these aren't in the cells, just like these ones. These don't extend the whole way of the cell, but they are in the muscle fibers. Here, this isn't in the muscle fibers, it's in the tendon. So when it feels, let's get our sensory. So we have our sensory neurons, then we have our motor neurons, right? So our sensory neuron feels the tension, right? If this is contracting, it's going to feel the tension right here on the tendon. So what it's going to do is it's going to signal these other cells. So we're going to signal, it's the exact opposite. So instead of signaling the quadricep, it's going to signal the hamstring, cause a hamstring to contract. So our hamstring is going to contract. And then it's going to cause IPSP. This was EPSP. It's going to cause IPSP to the quadricep, causing this to relax. So the reason it does this is it doesn't want to contract too fast. So this maintains and balances the forces. That way we don't break bones, and our body is able to maintain a healthy equilibrium in how the muscles pull. So one more thing I wanted to go back to that I forgot to talk about real quick for our tonic and phasic smooth muscles. We talked about MLCK and we talked about MLCP. So MLCK sometimes is referred to as a snake with its tail in its mouth. It's in a conformation that it doesn't activate. So we have calmodulin here. It has these calcium receptors. So when calcium comes and bonds to this, it goes to, attaches. We have to have all 4 binding sites with calcium. It's going to bond to this MLCK. So here's our calmodulin down here. Here's our MLCK, and now it's activated. And now it's going to be able to add a phosphate to the myosin head. For our MLCP, we're mostly worried about deactivating it. We'll call it Pac-Man. So it's gonna go and it's gonna eat those phosphate links, right? So we can add rho kinase. And rho kinase is gonna add a phosphate here with ATP, which is gonna cause it to be closed, which means it's not going to work. Rho kinase is signaled by something we don't know, which is signaled by calcium. So when calcium increases, it's going to turn off these rho kinases and enable the cell to undergo tonic. That's why the tonic requires, right here we talked about how the tonic requires this DHP, this extra source of calcium, because of maintaining the calcium is going to allow it to stay closed in this latch phase. And so this is the way it turns off the MLCP. Or activates it sooner. So sorry, I just messed up my words there. This is activated sooner in the tonic form, but that's how in phasic it waits, is it turns off more of these rho kinases because there's a sharper spike of calcium coming into the cell. I believe that's everything. Let me read the question one more time. Okay. I believe that is everything. Thanks, Aaron, for watching. Hopefully I wrote enough you can just zip through the video and you don't have to listen to me talk. Okay, perfect. That's everything. Thanks.